This tutorial is designed to help you better understand how to make some very basic, beginner's level free body diagrams. They're simple diagrams used to represent forces acting on an object, and then we're going to interpret those diagrams to discuss the resulting motion. Please remember, these are basic, beginner's level. When you get into higher level physics, you'll be able to have some more complicated interpretations of these same simple diagrams. Let's get started. In a free body diagram, we like to represent the object that's being subjected to these forces by a square. Sometimes you'll see them represented by a point or a dot, but in my class I prefer the square. Because we are on Earth, all objects are going to be affected by gravity. And gravity is abbreviated as F of G, meaning force of gravity. Let's just say that an object has a weight of 10 newtons. The weight of the object is really the gravitational force on it if you measure it in newtons. So we're going to write 10 newtons. This object is sitting on something. So there's a force that's pushing against gravity that we call the normal force, abbreviated Fn. It's always going to be equal in magnitude but opposite in direction. So it too is going to be 10 newtons, but it's pushing up, causing this object not to fall. The F of A represents the applied forces. So let's talk about how we interpret this diagram. If we want to calculate the net forces or the total of all the forces acting on this, we'll start like this. I prefer that my students start by grouping together their F of G and F of N because those are forces that oppose one another. They work against one another and they need to be subtracted. If they were working together, we would add them. So we have F of G, which would be our 10 newtons down. I like for you right now to show me that down arrow to prove to me that you understand that forces not only have a magnitude, but they also have a direction. We're going to subtract from that our F of N, which happens to be 10 newtons up, and then we're going to combine the rest of our forces. Now let's look at our F of A's. We have our larger F of A, which is 10 newtons, and a smaller F of A, which is 2 newtons. Start with your larger, which is 10 newtons in that direction. And because these forces are acting in opposite directions, they're oppositional, so we're going to subtract them. We're going to take away the 10 newtons in the opposite direction. But we're not finished. We first need to see if this object is going to accelerate in one direction or the other. Common sense tells you if one guy's pushing very hard and the other one's pushing with less force, the guy that's pushing the hardest gets the object going in his direction. So the direction of the motion is going to be like this. Once we know the direction of the motion, we know that there's going to be friction, specifically kinetic friction, that's going to be acting in the opposite direction, because friction always opposes the motion of an object. It gets in its way. It tries to stop it. And for our sake of making things simple, let's have friction just be 0.1 newtons. So now let's go back to our net force. Now we have to subtract what friction is doing to this. And now you should be able to do the simple math. The F net here, these cancel each other out. 10 minus 2 is 8. 8 minus 0.1 is 7.9 newtons. And we already know what direction it's going, so we add that to the end. We learned before that if your net force is not 0, then your object has been subjected to unbalanced forces. All unbalanced forces result in the object accelerating. So that's the interpretation of our first diagram. Let's move to a different diagram. All right, diagram B. Again, we're going to use the 10 newtons as our gravity. It's opposed by another 10 newtons of force in the upward direction. But here we have our F of A's, which happen to be our applied forces, pulling in opposite directions on this object. So let's take a look. Right here is where we made sure that we combined our F of G and F of N. They are oppositional forces, so we need to subtract. Then we're going to combine all the other forces going on. In the last screen, I told you to pick your largest force. Well, we've got equal forces here, so it doesn't matter. You're going to take 10 newtons in this direction, minus 10 newtons in this direction. Because we don't have a direction of motion, we are not going to incorporate any frictional forces. So this is all we need to have. And if you add all those up, you get 0. When you have an F net of 0, then you are going to have balanced forces and you are going to have no acceleration. My whiteboard freaked out there for just a second. All right, let's go to the next example. Okay, here we have where we have some cooperation amongst those F of A's. All right, we're going to have our gravity pulling down with 10 newtons. That means our normal force is going to be pushing up with 10 newtons so that the object's not falling and it's not moving upward. To calculate our F net, we're going to start by combining our F of G and our F of N. They're opposing, so you have to subtract them. Make sure you put your arrows for me because that's showing me you understand the direction of the force. Now let's look at our F of A's. We've got 10 newtons going one direction, 2 newtons going in the same direction. They're working together. So we're going to add those together. Doesn't matter which one you start with. We've got 10 newtons in that direction, added to 2 more newtons in that direction. And before we're finished, we need to figure out, are we going to be able to put any friction in our particular free body diagram? We should be able to note that the motion of the object is in this direction. That means our frictional forces are going to act in the opposite direction with our made-up friction of 0.1 newtons. So down here in our F net, or our net force, we're then subtract that 0.1. Because remember, that friction tries to interfere with motion. So now when we do our calculations, as usual, F of G and F of N cancel each other out. And then we have 10 plus 2 is 12. 12 minus 1 is 11.9 newtons. And we've already determined the direction of the motion that way. That's our net force. So whenever you have a net force that's not 0, that means that the object has been subjected to unbalanced forces. And when you have unbalanced forces, you have an object that is accelerating.